Hello, everyone, and welcome to the UFS webinar. This webinar is hosted by the NWS OSTI. The goal of this webinar series is to enhance communication and shared advancements in all aspects of the UFS, both in research and operational settings. I'm Stacy McKell, and I'm here to help coordinate and deliver the webinar. Feel free to contact any one of us at OSTI if you have any questions, comments, or suggestions. Here are a couple of housekeeping items I'd like to share with you all. Second. So, having a little bit of difficulty here, just one moment. Okay. Well, okay, so I'm sorry about this, guys, but due to the high number of attendees, you'll be in listen-only mode. Thank you. You'll be in listen-only mode today. So if you have any questions, okay, you will not be able to unmute. If you have any questions now or during the event, please submit them via the Google document provided in the chat. The presentation lasts about 45 minutes, followed by questions and answers for 15 minutes. Today's webinar is, excuse me, will be investigation of land-atmosphere interaction in UFS and its influence on model mean bias. Before we get started, I wanted to quickly show you how to sign up for the webinar notifications and how to view archived information. So what you do is go to the portal at ufscommunity.org, scroll to the events section, and you'll see the webinar listed on the page. Okay. Past webinar events will be found also on the portal. All of these webinars will be recorded and made available on this UFS portal. Today's speaker was supposed to be Unkyo Seo, but I believe we're having a little bit of technical difficulties. So Paul Dirmeyer will introduce the speaker, and he will probably be presenting as well, unless we get Dr. Seo on. Okay, so Paul, take it away.
Okay, thank you. Let me get our window up here. Hopefully that's showing up. So yes.
It's blank now.
Oh, now we're not getting it?
Now we're not getting it. It's blank.
Okay. Same as before. Let me try it one more time.
There we go.
Okay. Let's see, is this the right one? And there. Is that looks right?
That is perfect.
Okay, here we go. So yes, Dr. Unkyo Seo was to be our speaker today. He is a postdoc working here at COLA for about the last year, but not working physically at COLA because of all of the fun we've had around the world with COVID. He's actually been working from South Korea, where he is, and he will be coming with his wife and young son in 5 days to the US. So I think he's in a bit of a scramble trying to get things put together and to make his move. The timing was a little bit unfortunate. And of course, it's the middle of wee hours of the morning over there. But I can take over and give his presentation on investigating land-atmosphere interactions in UFS and its influence on model bias, work that we've been doing along with Mike Parledge and Haylene Way at EMC and Michael Eck at NCAR in the Joint Numerical Testbed. This is all part of the land and land atmosphere validation component for UFS model development and R2O. So I think everyone here is probably well aware of UFS and the Unified Forecast System. Our particular focus has been on the role of the behavior of the land surface model and the role of the coupled land atmosphere system in trying to diagnose if the feedbacks are realistic. And in particular, you see highlighted here in red, the big transition from the land surface point of view, which has occurred going from prototype 6 to prototype 7, which is a whole scale replacement of the NOAA land surface model, which has been in UFS and prior to that CFS and GFS for I think well over 15 years now. Transition to the NOAA MP, the multi-parameterization version of NOAA, which is a considerably more sophisticated land surface scheme. Not the only change going from P6 to P7, but certainly a major change that we'll be focusing on. And other components here are ones that you have seen. So we've been sort of following along as these different versions have been, prototypes have been run in their standard test mode of 7 years worth of forecasts, initialized every 15 days throughout the year, so 7 times 24, 168 runs. And this creates a large enough pool of data for us to calculate statistics of land atmosphere coupling and feedback. And so you can see the progression here from prototype 5 when we sort of first came in, looking at prototype 6. Unfortunately, again, in time for this seminar, prototype 7 that was not completed. I heard yesterday that it's about 1/3 the way done, but we do have the earlier prototype 7A sort of sub-prototype, and we've been looking at that data, which is only 2 years and only for July simulations, but it's giving us a taste of what to expect, and we're certainly seeing some significant changes. As you can see, not only is there the change from NOAA to NOAA MP, but there's some changes in vertical resolution, updated orography, some other changes as well, including, as we'll show later, a change in the vegetation database that's used for the land surface model. So just a little background, because I know probably most of the people on call are not terribly familiar with the land surface modeling component. So what we have is for the original NOAA scheme, each grid cell, which underlies an atmospheric grid cell, is treated as a singular bulk surface with an active vegetation fraction and an active bare soil fraction. It's sort of what we call the big leaf model. You sort of treat the vegetation as one giant leaf covering the surface. Each grid cell then has a single roughness length, a single albedo. The soil underneath the vegetation is completely obscured as if the plants were right up against the ground. There's a single set of fluxes that are passed from the land surface to the atmosphere, single sensible heat, latent heat. Only one bulk surface temperature that's used for doing all calculations, whether they're radiative or sensible heat flux, what have you. And the snow is also a single bulk layer, regardless of the thickness of the snowpack. That in particular has a lot of issues for thermodynamics. There's no groundwater recharge at the bottom of the layer. Once water drains out of that bottom 4th layer, which is 2 meters below the ground, it's lost to the system. When we look at the NOAA MP model, it's still not, it's by far not state of the art in terms of complexity, but it has a lot more realistic treatment. Each grid cell has 2 separate tiles for vegetation and bare soil, but they are separated vertically so that soil under the vegetation does interact with the atmosphere. Each tile still has a single roughness length and a group albedo and emissivity, but there are different exchange coefficients for each of the fluxes, and they're different for the canopy and for the soil. There is an iteration for the heat fluxes to try to get convergence. That was in the old version of NOAA as well, and as implemented operationally, it was truncated, very short sharply to prevent the runtime from getting too long if it was taking a lot of iterations. That created some energy imbalance problems. They're better treated in NOAA MP. So the iteration goes on, and we have a total sensible heat flux that's returned that's a weighted average of the individually calculated components. In a boundary layer scheme that only requires the fluxes, that's not a problem. Nonlinear processes for averaging these different exchange coefficients can create issues. There's not a single surface temperature in NOAA MP. Leaf and canopy air and soil surface below canopy, they all keep their own temperatures, their own heat budgets. The snow now has 3 layers, a thin surface layer and then thicker layers below that, which gives much better thermodynamics and melting characteristics. And there is the option to couple to a groundwater module so that there can actually be interaction and recharge. Water can get from the groundwater when it's shallow back up into the soil column and re-evaporate. 2 surface temperatures in UFS. NOAA originally had the single component to that. In NOAA MP, a bit more sophisticated. And unlike NOAA, there are different source temperatures for the sensible heat flux calculation versus the long wave upward long wave radiation calculation. And so the emissivities have to be averaged in a different way, and those coefficients depending on which way the calculation is done. Again, to try and make it more realistic and attain better closure. And this just is a quick show of some of the improved performance when run at single points for early development of NOAA MP, a much better simulation of diurnal cycles, as well as synoptic variability. Won't belabor this too much, but basically the red line NOAA MP fits the green dots much better than the old system. Just the physics are a bit more realistic. And again, this is showing something quite similar in that regard, that the MP version has more realistic exchange coefficients, and it results in a better simulation of diurnal cycle. In this particular location, particularly getting the daytime maximums simulated much more realistically. I'm going to skip ahead so that we can get to results from UFS. So for comparison, we're really looking at the P7A sub-prototype, which has a very limited number of simulations from only 2 of the years. We look at the whole 31-day model forecast period for those 2 summers, so that gives us a couple of full Julys, fully realizing that there is drift in the model once you get out 31 days into the forecast. The climatology is not identical to, say, day 1. That's something we'll be able to look at better when we get to the version 7. But for now, we have no choice but to ignore that and to plow ahead. First, looking at the soil moisture mean climatology, and most of the maps I will show will focus on the conterminous US. Here we're comparing to a large number of available in situ soil moisture monitoring sites across North America, well, across the continental US here, from the International Soil Moisture Network, ISMN. And this actually combines information from a number of different independent networks into a single database. There's a lot of states that have their own networks, their regional networks, as well as a few different national networks that are operated by different agencies. The USDA, for instance, has one network, and then in SNOTEL in the Western US, it has a different management. And what we see across the bottom, and we'll kind of repeat this throughout, is prototype 5 on the left, prototype 6 in the middle, and where we expect to see a big jump to prototype 7A on the right. And what's shown here are on the bottom are the biases or deviations from the in situ means for July in these locations. So on the bottom, red is where the model seems to be running a bit too wet, and blue is too dry. We do see some changes that in this case, it looks like there's a bit of an increase in the bias and as well as the root mean square error in P7A. But a very key point is that it's not so much the absolute value of soil moisture that's important in a coupled weather forecast model. It's whether this is going to produce the right fluxes and the right flux variability that couple to the atmosphere. But here we do see kind of a homogenization and less regionalization in the errors. There's a big change from NOAA to NOAA MP is also the use of a more up-to-date land cover data set. And what's shown here is over sort of a portion of North America, what we had before in the original NOAA model, which was based on MODIS map on the top, where you can see the different vegetation types, and the key is on the left, sort of color-coded. Reddish colors, reddish and oranges are forest areas. The sort of paler orange is for the shrublands and so forth. Yellow, which you see quite predominant in a lot of the map, is grassland, and the sort of light orange is cropland. Those are a couple of the areas where we tend to expect a lot of land atmosphere feedback, and it's an area that we'd really be concentrating on for hopefully improving systematic biases in the model in those locations. Here we kind of zoom out to look at the global version of this, and also to show where we're looking at validation. For fluxes, we have the global FluxNet network of flux towers, which give us daily and actually 30-minute values of surface latent and sensible heat fluxes. A lot of the radiation terms, not all sites have all the radiation measured, but usually they'll have at least the shortwave measured, and about half of them have downward long wave and upward long wave as well. You see a lot of stations in US and North America, a lot in Europe as well, another place we want to validate, and quite a few in Australia. Those are some of the largest concentrations, and we sort of focus on those regions. You'll also see something, a recurring issue. Oftentimes the landscape type right where they put the flux tower is not representative of the larger area around it. And so in these maps, we mark where the FluxNet reported land cover type matches the data set that we're using in the model. We put a circle, and where they're different, we have a triangle, and there's various degrees of difference. But a lot of times, for instance, ecologists tend to set up these FluxNet sites. They're very fond of wetlands for some reason. They like to put their towers in swampy areas because they're really measuring, CO2 and biomass accumulation, which is not what we care about in weather forecasting. So their towers are in wetlands. We don't really have wetland grid cell types at a 1/4 degree resolution. It's not really realistic. So we have some discrepancies there. This is showing incoming net radiation climatology, the biases and root mean square errors. A very core problem that we have a lot of times in coupled land atmosphere modeling is that if you deliver the wrong net radiation to the land surface, it has to do something with it, with the excess radiation, or to make up for the shortfall. And invariably, that's going to affect the fluxes back to the atmosphere. So it's a garbage in, garbage out situation. So we wanted to see how well the model was representing downward surface fluxes. In this case, we're looking at the net radiation at the surface. And so the in situ observations are identical and always the x-axis. So this is at the FluxNet sites and where we have in situ radiation from the baseline surface radiation network as well. The y-axis is whatever we're testing against. In this case, the left side, we're testing against the Ceres satellite-based product. So this gives us a sort of minimal level of uncertainty, because we think Ceres is pretty good, but it may not match exactly with a flux site, because the Ceres also has a footprint in the pixels from the remote sensing. And so we see a bias of about 1.3 watts per meter squared across all these FluxNet sites, and a root mean square error of about 11.5 watts per meter squared. And then the next 3 panels are for the various versions of UFS as we're going through prototypes. And what we see is actually over time that the bias has gone over these locations from a positive bias of about 8 watts down to a negative bias, in fact, of about minus 5.5 watts. But we do see a consistent reduction in the root mean square error, and the lowest values are for the P7A. So that's hopeful in terms of getting less garbagey input from the available energy at the surface. Relatively low bias, and in fact, if we also look at, and this is sort of summarized on the table on the lower left, the red highlighted areas are the ones that have the better biases and actually the better root mean square error as compared amongst the 3 different UFS versions. So we're glad to see, at least in this small sample, P7A is looking pretty good. And also, not shown here, but when the vegetation types actually match, then we actually get even better statistics, which is good. That means having the right vegetation type in your land surface model matters. It's making some improvement. Surface albedo is another one. The albedo climatology that's used. We see a lot of spread in these locations. Albedo can be highly variable on small spatial timescales. There's even a lot of RMS error even in the series product, and that's mostly because of differences in scale. So this gives us an idea of, okay, we know we can't overcome differences in scale, but we're well within bounds in this case. The bias for albedo has gotten a little bit higher over time. Depends where you look. If you look in places like the Sahara, it's actually gotten lower, but there's no flux net sites in the Sahara because there's no vegetation. And again, the ecologists like to set up the flux towers. We're always asking them, could you put some in the deserts? We need measurements there, but they're not interested. Anyhow, here we do see not much difference between P6 and P7A, but generally speaking, a little bit better for the P6. Not a terribly large difference in these particular locations, but certainly over the grasslands and the crops, we're seeing significantly lower RMS errors. And that's very important because those are the vegetation types where we tend to see the strongest land atmosphere feedbacks. I'm here looking at the incoming net radiation globally, and just to give you sort of a global picture of what it looks like. Here, all the biases are relative to series, the series product. Again, only looking at July 2012 and 2013. We can see on the top row is net radiation, the middle row is the net shortwave at the surface, and the bottom is the net long wave. What we see overall, and again, the sign convention here for series is negative long wave, means upward long wave. So negative is upward, and so all the blue colors you see across the bottom is excessive upward long wave radiation at the surface. We also see in a lot of those same locations excessive net radiation. So it's really the land surface is heating up because there's too much energy coming in, and then it puts it back out. The short wave is maybe more interesting, the net short wave, which is really mostly a measure of the downward shortwave radiation. We see positive biases in most locations, which is largely indicative of either insufficient cloud cover and or insufficient scattering by aerosols in the atmosphere, so that we've got, again, a bit too much radiation to deal with at the surface, and then the land surface model has to do something with that. So this is the net shortwave radiation biases and root mean square error. So there's increased shortwave net radiation in P7A. Over the Sahara Desert, we see this big blue blob here, which is indicating this decrease in the surface albedo in NOAA MP. You also see a bit of a decrease over Greenland, which seems to be indicative of a different snow or ice albedo in that location. Other locations see mostly pale pinks, so that's a slightly increased albedo in a lot of other areas. That's helping to offset some of the extra downward radiation. The decreased long wave net radiation is related to that upward long wave that I showed in the last panel due to the increased surface temperature. And in NOAA MP, we're seeing that kind of globally. Although in the US, the bias in the Great Plains is a bit reduced, and we'll zoom in on that in the next panel. Or in the next panels. Here's the temperature, daily maximum temperature, mean climatology. So the CPC max temperature in the upper left over CONUS, and then again, below that, P5 on the left, P6 in the middle, P7A on the right. The overall Tmax average temperatures for July are in the middle row. The bottom row shows the bias. And what we see is not much difference from P5 to P6, but a big change in P7. That large, warm, positive bias, afternoons too hot over the Great Plains and agricultural regions of the upper Midwest has pretty much gone away. but we've traded that for a little bit of an intensification of warm biases over the southeast US. Some of the other biases still remain, still a bit of a cold bias in the northern Rockies. We still have a positive warm bias in the central valleys and of California and up into the Pacific Northwest. I wouldn't hang our hat too much on it because it's still only 2 years. We really want to see what the full P7 looks like before we draw too strong a conclusion in terms of whether biases have gotten worse or better. But as I'll show later, we have a pretty good handle on actually what's going on and what's causing these changes. Here's the mean precipitation climatology over the same region. All the UFS prototype simulations have positive precipitation biases over sort of the upper Mississippi Valley and especially over Colorado. For some reason, UFS wants there to be rainforests over Colorado, you know, the lush tropical forests of Boulder. Sorry, they're not actually there. And then a bit of a dry bias across Texas and a lot of the kind of the southern Midwest and the southeast. And this seems to still be there. It's not really going away as we make the change in the land surface from P6 to P7A. Now, the interaction part. This is sort of standard meteorological variables, the things that we typically like to try to forecast and get them right. What's going on process-wise here? And this is where the land-atmosphere interactions are important. And we have metrics that we can use, multivariate metrics that relate a forcing and a response, or a source and a target, if you will. And the tropical or the terrestrial coupling index, TCI, is a way to sort of combine these effects. It's basically, say, we think that soil moisture is controlling a surface flux, and so this coupling index is the correlation of those two in time, daily, day-to-day values of correlation, multiplied by the standard deviation of the effect of the, in this case, the flux. And so that tells us both whether there is a strong relationship between the two and whether the magnitude of the variability is large, because we need those two components in order to force a response in the atmosphere, say in the boundary layer properties or in the formation of clouds driving precipitation. And it very much depends on the range of the soil moisture. When you're in a very wet location, you have plenty of soil moisture, then transpiration is not constrained by the availability of water in the soil. What constrains constrains fluxes then is the amount of net radiation you have, the amount of energy. And so that's an energy limited regime. Below a critical soil moisture, then you start to get a transitional region where soil moisture is controlling the fluxes. And as you decrease soil moisture, latent heat flux evaporation will also decrease because there's not enough moisture, and sensible heat flux will increase to compensate. And then below a wilting point, basically there's no soil moisture available, and then you're in kind of a very critical dry zone like you would have in a desert region or during a drought, in which case everything goes into sensible heat flux and you get a big amplification in temperature. A very key aspect of transitioning into severe drought or heat wave regimes is crossing over that wilting point in a location. So we can look at this, and we're looking now not only at the FluxNet sites, but some gridded products, observationally based products for surface fluxes, as well as for global soil moisture that are remote sensing based as well to give us large scale coverage. So this shows that terrestrial coupling index between soil moisture, latent heat flux. So in this case, the x-axis is the in situ observations at FluxNet sites. The y-axis, the left two are from gridded estimates of that come from remote sensing. Again, how good is our sort of global gridded product compared to in situ validation? The left is the Gleam flux product with the CCI combined satellite soil moisture product. B, the second panel, is FluxCom, a different set of estimates of fluxes. Instead of being based on process level land surface model, it's based on machine learning. And then the UFS P5, P6, and P7 once again. The colors of the dots indicate the vegetation category in these sites, and this is all over locations in the US and Europe predominantly. And so what we see is a really sharp reduction in the bias when we go to P7A and using the NOAA MP model. And the RMS error has dropped by about 15% as well from what we had in P6. So that was a really good sign, I would say, for us. And it's getting down close to within the realm of what we have from these other gridded products as well. So that was a very helpful point. And you can see here again in the table, the red values are the lowest or the best fits among the UFS types, and P7A is doing very well across when we look at all vegetation types, as well as in forest and again in grassland and crops. So this is something we wanted to see. This is just looking at the correlation component of it, how strongly correlated the two are. And here again, we see that there's a much more realistic correlation between soil moisture and latent heat flux in P7A. I wouldn't say much. There is a better fit in the correlations with observations in P7A than the other versions. So again, more sophisticated land model is doing better. And then the standard deviation, the variance of latent heat flux. Here, not quite as impressive. In fact, there's a bit of over variability and some larger root mean square errors in the variance of latent heat flux, which we think might be tied to the excess energy that might be driving it, but we haven't quite pinned that down here. The overestimations over the shrublands, for instance, leading to very positive TCI bias in that location. Not a lot of shrubland in the US, but that becomes a big issue in subtropical regions. Land-atmosphere interaction now is a map. Now comparing the maps of GLEAM in the upper left is what we think has probably the best fit with observations. So we'll use that as our whole US category picture. So we see that picture of that coupling index, which according to the GLEAM CCI should be strongest in the Great Plains and into the Rocky Mountains, especially the Southwest US, and weakest in the Southeast. And P5 and P6 show a very strong land atmosphere coupling blob, that dark purple area, which happens to almost perfectly outline the crop land cover type in NOAA. And this is a problem we've known about for a long time in NOAA, that over the crop vegetation type, it's just way too strongly coupled to the atmosphere and way too prolific in its degree of evaporation with respect to soil moisture. And we see that's greatly ameliorated in P7A. Still, the maximum wants to be centered over Missouri instead of over the Western Great Plains and High Plains a little bit shifted, but certainly a step in the right direction. And we're picking up a lot more in the Southwest. It does tend to want to put the weakest values in New England, which actually, if we look at other observational data sets other than GLEAM, it kind of tends to sometimes agree with that. So again, this might be a sample size problem. And then we can see the biases below. There seems to be this erroneous hot spot sort of over the central Mississippi Valley. And a very nice plot that Unkyo put together that kind of summarizes how errors propagate, and sometimes they'll cause problems and sometimes they don't. So on the left side here, we're looking at precipitation. The top row is what we saw in P6, the bottom row is P7A, and the precipitation biases now relative to the MSWEP observational product. We see the biases in P6, how they're scattered, and in P7 we have now developed, at least for these 2 years, a wet bias over the northern Great Plains and the upper Midwest, and then a bit of a dry bias from Texas across to the Southeast US. In surface soil moisture, where before we had this overall dry bias throughout the NOAA in version P6, we now have a wet bias where we have the wet rainfall bias, and actually almost no bias at all in the Southeast US. So that lack of rainfall seems to be compensating with something, and we're getting actually a fairly small bias in soil moisture. And then when we put on top of that the available energy energy balance, we see that our coupling index now has ameliorated the overcoupling in the upper Midwest. And we're getting now a little bit of a stronger coupling in the Southeast, maybe a bit stronger than it ought to be. Certainly true in sort of the central Mississippi Valley. And that is now leading us, we think, to that warm bias that we're seeing now in the Southeast. Whereas on the other hand, that really warm bias that we had before in the Great Plains and the Midwest has gone away and in fact turned into a slightly cool bias. Again, this is sort of a process linkage. It helps us to understand how these errors propagate and which ones are important where. And it very much depends. That Southeast region is a location that has a very different sort of coupling. In the upper Midwest, high Great Plains, Nebraska, South Dakota, across into the Corn Belt, essentially. That's that transitional, mostly agricultural region where we do have a lot of control of soil moisture on surface fluxes. And there, the increased rainfall and the increased soil moisture is increasing the latent heat flux. It's decreasing the sensible heat flux. It's an area, it's now a region with a little bit weaker land atmosphere coupling because it's not so hot and dry, and that's cooling the air surface temperature. And we see that very clearly if we look at the soil moisture and the latent heat flux in those locations, the actual values and the biases. In the Southeast now, we have a little different situation. That's a very humid region, mostly forested, typically not very responsive to variations in soil moisture. So that decrease in rainfall, it did not change the soil moisture too much. A little bit of a decrease in the latent heat, a little increase in sensible heat, not much change in the net radiation, but it did tip us over now into a bit of a stronger coupling regime. And thus now we're having a warmer surface temperature. That positive feedback is coming into play. And then the energy balance terms, we see that now in P7, we're underestimating the latent heat flux in that region. And by about 10 watts per meter squared, overestimating the sensible heat flux by about 10 watts per meter squared, it just tipped us over into that sensitive regime now, that transitional regime that we weren't in before. And as a result, now we're getting some compounding errors in surface temperatures. So to summarize, this study investigates the land atmosphere interactions in the UFS prototypes from P5 up to P7A. We have the machinery in place now. When the full P7 is available, we can look at that. When P8 comes available, we're ready to look at that. The main difference we see in P7A, or the main difference in the transition to P7A, is the land surface processes and the replacement of NOAA with NOAA MP. And so, just summarizing here, the differences that are inherent in the models: the land surface tiling, snowpack, which is obviously not a July problem in the US. We haven't had a chance to look at the winter side yet. We're kind of waiting for the full suite of P7 before we can start digging in, because even January is not a good season to look at. We really want to look at that transition into springtime and the snow melt. That's going to be really crucial. I'm very curious to see what March and April look like in a lot of the world, and May at higher latitudes. We really want to look at that. And then eventually plugging into groundwater, which is not really an activated component yet, I don't believe. The modeling states that are related to land atmosphere interaction, we've evaluated a lot against in situ observations where we have really good point measurements, but maybe don't represent the scale of the grid cell quite so well. And so we've also been comparing to other gridded products so we can get a continent-wide picture of what's going on. Generally speaking, we see that net radiation is doing better in P7, P7A anyways, and there is some underestimation in forest. The surface albedo, there we see some big changes with the change in the land surface model. Generally an increase in albedo and MP in the vegetated areas, and that seems to be doing well. The big decrease in albedo over the Sahara, we have a lot of difficulty not having good observational data to validate whether that's having, what the process impact is. We can certainly look and see what's happening with temperature biases in that location. Surface soil moisture biases are still there. They've moved around a little bit, but the real key is what's happening to the surface fluxes, and then what's the response in things like rainfall and near surface air temperature. There's still this persistent wet bias rainforest of Colorado problem we're seeing in UFS. I'm not sure how that's going to be addressed. There's probably, looks like an orographic component to that. Otherwise, wet bias in the northern Great Plains, and at least for the 2 years we've looked at, dry bias in the southeast. Again, tentative conclusion about those biases, we need to see more years of simulation. Surface air temperature, big improvement in the warm biases over the Great Plains and the agricultural regions. We've swapped that for a bit of a warm bias in the southeast. Again, let's see what 7 years and a lot more runs look like. And then our coupling, definitely we're seeing better land atmosphere coupling behavior, more realistic behavior in P7A, and things that we're not showing here, but we've looked at a lot more of the processes going up into the atmosphere as well and trying to synthesize what's going on in terms of the bigger picture of the wiring diagram, if you will, between land surface and the links in the process chain to fluxes, near surface properties, boundary layer development, clouds, and precipitation. That is it. Thank you for your attention. And I will try to answer questions as they come. If there are things that are down in the weeds that Ankyo did and I may not understand, I might have to defer. Thanks again.
Thank you so much. Thank you very much, Paul. So we do have a couple of questions, and if you are able to pull up the questions doc, if you look on the chat, you'll be able to pull up the questions document. Or
okay. So the Google Docs?
Yes.
Yes, okay.
And you will see the questions listed.
All right, I see 6 questions. They're all anonymous. Okay, at least as far as I know. For the surface solar radiation albedo biases, the first question, of different model setups, how much does this come from difference in land type maps and how much come from different physics between NOAA and NOAA MP? That's an excellent question, and that it sort of requires a sensitivity study. We need a 2x2 contingency matrix where we only change the physics and only change the vegetation type. I'm not sure if Mike Barlage is on the line, he'd be able to speak to that. But no doubt it's both are probably contributing in certain locations, but given that we've changed both things at once, we can't really separate out that quantification. Question 2, for the latent heat flux in the terrestrial coupling index calculations. Is it the grid level latent heat flux it has above the canopy? And if so, how would the vegetation evapotranspiration affect this? That depends on what's being reported in the model. Typically, the latent heat flux it's the composite of transpiration and soil evaporation and canopy interception, all combined together. So in effect, it's kind of mixing in a way evaporation sources at different locations, if I understand correctly. Now, as for what's the specific contribution of the vegetation transpiration, again, that's something that would require delving into the individual components, which we did not do because we don't have that separated out in our observational data. The FluxNet sites don't, they just give us an overall latent heat flux or an overall evaporation rate. So for validation purposes, we stuck with the variables that we had for in observations for validation. So again, unfortunately, I can't answer that, but no doubt that's important for the processes, whether the vegetation is controlling the evaporation versus what's direct evaporation from water on the canopy or water in the soil. Question 3 says, nice presentation. Oh, it's from Tilden Myers. He admits to it. 2012, thank you, Tilden. 2012 was a drought year in the central Midwest. Could that have induced any biases and results since some of the land surface model drivers are climatologically based? Absolutely. And the choice of 2012 and 2013 as for the interim runs, I'm not sure where that came from, but that was not, I don't know if it was based on the fact that that was an outstanding year, but those were the 2 years that they used for the interim steps. Once we have 2011 through 2018, we'll have a much better picture of whether 2012 was an outstanding year or not. But that's certainly a viable hypothesis, I would say. Question 4, with the improvement in surface temperature and the coupling index in P7A, do we see a response in non-precipitating boundary layer clouds like shallow cumulus? We have those statistical outputs, but we haven't delved into it because we've looked separately at precipitation and cloud cover, or at least total cloud cover. We don't have it broken out based on shallow cumulus versus deep cumulus versus stratus. But so that's there to be looked at, but we haven't delved into that yet. So thank you for bringing that up, and that is something that we will definitely look at. That's something we expect, in fact, because the strong coupling with whether the partitioning between sensible and latent heat flux can have very different responses in how deep we build the boundary layer and how unstable the boundary layer is, which all connects to the convection, to the cumulus, whether it precipitates or not. So yes, that is definitely a direction that we are looking. Question 5, is irrigation represented in the model? And if so, how? Easy answer, no, it's not represented in the model. That is something that the only way irrigation comes in is that actual irrigation affects the actual near atmospheric properties like temperature and humidity. So if those data are assimilated to initialize the model, then it kind of creeps in a secondary way. When we get to the point that we're actually directly assimilating observed soil moisture into the model, and by observed I mean satellite soil moisture products, and this is something that that Clara Draper and team are working on at NOAA in PSL in Boulder, and also through the JEDI system. Eventually there'll be the land data simulation as well. Then that will be seeing, at least to initialize the model, it will be seeing the effects of the irrigation because that will be in the observed soil moisture. And then it will get in at least as an initial condition. But it's not represented currently in the implementation of NOAA MP as part of the physics of the model. That is something that some other land surface schemes do, and it may be something that, certainly something worth looking into in the future, because in places like California, or in the Western Plains where they do a lot of center pivot irrigation, you know, the Texas Panhandle and so forth, that could be a big element. Oh, people are going back and putting their names. Thank you, that's great. Question 6, is groundwater induced included in the model? And if not, what do you expect to see regarding the impact of including groundwater on the current bias patterns? I am not confident enough to answer whether that's being represented in the current implementation or not. I know that's a big issue is how you initialize the groundwater for these forecasts. And I know that Mike Barledge and crew several months ago were going through that, how to do that or how well it's being done. I would kind of punt that question to Mike to answer because he knows about the model physics much better than I do. But certainly, places where you do have shallow groundwater or riparian zones in particular, if those are being resolved properly, and they would be in a high resolution model, that can be a really big impact and have a big effect on total latent heat flux in a region. Oh, good, he's typing. Mike is typing in the answer. He says, currently, yes, it is represented, but only in a one-dimensional way. There's no lateral flow, so we don't have any of the lateral transport, which if you're running it at 364, maybe that's not a problem. If we get up to higher resolutions, that lateral transport becomes a bigger and bigger part of the water budget. So something to think about when we go or doing when we replace the high-res rapid refresh model, for instance, that may be something ought to be there. Question 7, prototype 7 shows improved land-atmosphere interaction. I hope somebody's keeping an eye on the clock and they'll tell me to shut up when the hour's over. Shows improved land-atmosphere interaction, but the sample size is small. Yes, the sample size is small. we've only examined over the CONUS region. We have looked elsewhere a bit, but we've definitely focused on the CONUS region. We've also looked in Australia, and we've looked quite a bit in Europe, where we have a lot of FluxNet stations. Have we seen similar improvement in land-atmosphere interactions from the NOAA LSM to NOAA MP in other models? I'm not sure what you mean by other models. What are the major contributing factors? Or maybe you mean in other regions. In other regions, we certainly, I think we did see improvements in Australia, agricultural regions in Australia. Over Europe, I'm trying to remember what we saw in those locations. I mean, it's really, we really would like, the issue about a small sample size is absolutely crucial, and we do want to look at more years, and particularly years where we can look at situations where we know we have a drought or we know we have a heat wave, like 2015 drought situation in Europe will be a very good one. So those are, other models like WRF. Okay, I see. Yeah, I think that the improvements are fairly comparable. But I'm speaking very subjectively. I couldn't put an objective number on whether the improvements are comparable to what we see in other models. Certainly the physics are more realistic, so it ought to be better, and if it's not, it's probably a matter of either we've exposed other sources of error in the model that were tuned away before, and or we need to do calibration and validation further on the model. I mean, this is really, 7A is the first time the NOAA MP was put in, and there's a lot that can be done probably in terms of some parameter adjustment. And question 8, which is being typed as we speak, so I'll give a moment for the person to finish. What do we think about forecasting soil moisture using offline NOAA MP forced with corrected meteorology such as UFS V12 fluxes? Now that's sort of the old school way of initializing the model, is you kind of have a running what we used to call LDAS, land data assimilation, where there was actually we weren't assimilating anything, but really just driving the land surface model offline with analyzed meteorology, and doing that kind of over time, and every day you update it with the most recent meteorology. That is still kind of, I think it's a viable way of at least setting up your first guess, but ultimately, I think the way we're going is the right way, and that is to have a coupled analysis system, land and atmosphere together, along with the coupled DA. We're doing data assimilation of the atmosphere, but also the land surface, particularly soil moisture. And then ultimately, vegetation is another thing that has a lot of interannual variability. You have a drought, the vegetation goes brown, senescent, that has huge impacts, not just on the water budget, but on the energy budget. You have a cold spring, and so then the green up happens 2 weeks later. If you're using climatological vegetation states, you're going to probably have some big temperature biases for a couple of weeks, because the model says, oh, everything's green and dark now because it's April, and in reality, the vegetation hasn't greened up yet. So these are the kind of things that I think will also lead to further improvements beyond what we're doing and what we're capable of doing just in P7. Q9 is another question for Mike Barlage to answer, and he's typing away, yay. How many spin-up years to get the initial soil moisture conditions? How long do you have to spin up the model in order to get it? And Mike Barlage says at least 10 years. And that's what they have done. And yes, that's a question. And that depends on depth too. The surface soil moisture spins up quickly, but for the deeper layers, the deeper you go, the longer the time scales. Just like in the ocean, the deeper you go, the longer the time scales. Q8 is being updated as an interim solution before coupled DA. Yes, all we kind of have is the LDAS approach, where we the land surface scheme offline and driven by observed meteorology, and try to use that as a best guess. But again, we do have the problem then that the coupled models behave differently than they do when they're uncoupled. And coupling the land surface model in with the UFS atmosphere it reaches a different balance than either would individually. So that will continue to be a problem as long as we do the old-fashioned LDAS way of initializing the model. And it can cause spin up and even shock problems in the early parts of forecasts, unfortunately. Okay, I think everyone's exhausted and it's 3:55, so somebody rescue me. I think we're done.
Thank you so much for that, Paul. This was very interesting, and you see a lot of people are interested because they have lots of questions.
Yeah, that's great.
It is
There's probably
absolutely
lots of questions because I didn't do a terrific job of communicating what Unkyo would have communicated, but hopefully it got across.
Yeah, well, yeah, we thought he was going to be here, but okay, but you did a great job. Thank you very much for that. Okay, we're going to wrap things up now, and I will have these questions emailed to you and Unkyo if you
Excellent.
can, fill them out. Answer them accordingly, that'll be great, and then everybody will have access to them. Thanks everyone for attending. The next webinar will be held next month, October, I believe it's October the 14th. And that will be on CCPP. And the speakers will be Leisha Bernadette and Mike Eck. You all can register for the webinar once the announcement comes out. And also you can subscribe to get future announcements. Thanks and see you next month. Have a good day.